Hello and welcome to the course Machine Learning for Robotics and Computer Vision. My name is Jens Belay and I'm the lecturer of this course, where we want to teach you the basics of machine learning, but also look at applications for robotics and computer vision. But first, what is machine learning? Here I give a classical definition by Tom Mitchell, which says machine learning deals with a computer program that is set to learn from experiences E with respect to some class of task T and performance measure P, if its performance at this task, as measured by P, improves with the experience. So this is a rather broad definition of machine learning, which covers the many phases of machine learning. But in a nutshell, the goal of machine learning is that you want to design algorithms that are able to extract valuable information from data via adapting a model. And this adaptation of the model is based on data, and this is what is called learning. But when we look at machine learning, then machine learning powers many of the things that you are having around in your everyday life. So for instance, things that are powered by machine learning are, for instance, the spam filters in your email program, so which decides between legitimate but also illegitimate emails, like called spam, which you don't want to have in your inbox. So here the task is to get some text, decide on the contents of the text and the context maybe, what is a legitimate email which you want to receive and which is something that you can filter out. And this is the spam classification task. But here, when we look also at when we are using our smartphones, then there's also a machine learning algorithm that solves some tasks. So here the autocorrection. So given some input, maybe some letters, the autocorrection automatically figures out some contextual words that will help us to type faster and to which we can then select. So here the task of the machine learning algorithm is to figure out what are sensible words that we might use in the next. And this is, of course, learned from a lot of data which you typed in or others typed in, and from this one can learn the contextual words that are meaningful for this message. But when we also look now in the pandemic, the streaming services that are used everywhere because we cannot go in cinemas anymore, and there a recommendation algorithm is used, which wants you to know about the series or the movies that you are interested in. And for this, the algorithm has to figure out from a lot of data, from viewings from other people, but also from your viewing experience, what is maybe something that you are interested in. But when we also look at personal assistances, like Google's assistant or Amazon's assistant, they have to recognize speech. So their speech recognition is driven by machine learning. So it has to transform our verbal command into something that is usable by the computer. And here the machine learning algorithms figures out what we said and transforms it into a text which is then usable by the algorithm. When we look at these tasks, so all these tasks, the autocorrection, the recommendation system, but also speech recognition are very hard tasks. So if you were tasked to just someone says to you, write a program to solve this task, it might be very difficult to write up some rules which you can use then to solve this task. So machine learning deals with this by getting a large set of data and learning from this data how to solve this task. So it's really a mechanism to give you the ability to just put in a lot of data and learn some usable, sensible tasks from this. But when we look at robotics and computer vision, there are also many machine learning algorithms at play that can give some information which is very hard to capture in a program which you would write when you want to write it. So here, for instance, self-driving cars. The perception systems of self-driving cars are mainly driven by machine learning algorithms. Here the system has to figure out what it sees in the surrounding. And some examples are like here on this computer vision task of object detection, to detect objects in the surrounding, something like the persons here or the sheep in the foreground. And Some other tasks is maybe also the semantic interpretation of images, where we want to assign each pixel a specific label. So that means a specific class, something like the ground, but also here the trees or the persons with different things. So, and as you see, these are very hard and maybe also not so well-defined tasks, but still we can learn some machine learning algorithms that gives us the answer in the end, which we are interested in. Talking now about the course, so what are the contents of the course? So we will have two parts. So in the first part, we will have the traditional machine learning methods, so where we want to teach you the basics, but also the machine learning terminology, but also some general machine learning models for classification, regression, and clustering. And this will be then the basis that we need to delve then in the second part into the modern so-called machine learning approaches, especially deep learning for vision tasks. So here we are focusing on the convolutional neural networks and how to learn the convolutional networks. But we will also cover maybe in the end some current research topics which are interesting. I'm not alone here, so I will be supported by Lucas in this course. He will be mainly responsible for the homework assignments, but also for the tutorials. Some words on the organization. So as you see, because of the situation, we have to record the lectures. So we cannot give the lectures in the lecture hall. So the lectures will be given by video recordings, which you watch at home in your personal speed. But we will also offer the option or the possibility to ask us questions in the tutorials, in a Zoom meeting. There we will also cover some practical aspects of the topics that we covered here in the course or in this lecture, and give some answers on questions. The course has an eCampus website where you find further information. There you will find also the PDFs of the slides, which you then can use for learning. The course will be supported by homework assignments, and the deadlines for the homework assignments are given on the eCampus webpage. And because of the situation, it's most likely that we will have an oral exam. So no, we will have an oral exam, but it's most likely that we will have it via Zoom. So that means we will not see us in person, but we will still have an oral exam. Some words on the homework assignments. For the exam admission, so in the end, for the oral exam, you have to solve at least 50% of all the points of the homework assignments overall. So that means when you have in sum, in the end, 50% of all points, then you're fine and you will be admitted to the exam. The homework assignments will be mainly coding tasks, so which will be handled in Python. So, and this is an essential part because there we will get some hands-on experiences on the more theoretical topics that we cover here in the course. The assignments and the submission will happen via eCampus, so you get the code that you need to fulfill the assignments on eCampus, but you will also submit it in eCampus. And one important thing here is you have to solve this task really alone, so we are not accepting that you're copying solutions from others. And as it's highlighted here, we also follow here a zero tolerance policy. So if we figure out that you copied solutions from someone else, then we have to expel you from the course. So the basis of this course are 2 books. So most of the contents are available in these 3 books. So one, the main resource of the first parts are the Mathematics for Machine Learning from Dijsselrood and colleagues, which gives you also some background on the mathematics for the machine learning tasks. So we will cover the basics here in the course, but if you have some, you forgot something about linear algebra or something like this, then this is covered in the machine learning, Mathematics for Machine Learning book. And the other book that we will rely on is the book from Simon Prince, which is Computer Vision Models, Learning and Inference. The good thing is the authors decided to make both books freely available, but this doesn't prevent you from buying the books if you really like them. So if you also maybe want to have this haptic feeling of having a book in your hand and that you can maybe scribble something down or something like this. So here are the URLs where you can get the PDFs. And on the slides, I will always reference to the machine learning, mathematics for machine learning books with MML, and to the computer vision books with computer vision MLI. So there you will see the references, where you then can look up in the PDF or in the book, which you have there to where the topics may be covered in more detail. So to end the introduction, so what is the goal of this course? So the goal, so as depicted here in this comic, is to not treat the machine learning algorithms as black boxes. So where you just put data in and hope to get the right thing out. So I hope in the end you will have a better understanding of the inner workings of the machine learning algorithms, but also on the things that you can tweak to get the machine learning algorithms to put out the thing that you are interested in. So that you are not like this guy just putting in data, trying to whatever, mangle with the data around to get something better in the end. So this is my goal, and that's hopefully what we achieve in the end. So, but now let's directly start with a high-level overview of the machine learning algorithms that we are covering in more detail in the upcoming courses. So the main components of a machine learning algorithms are the data, the model, and the learning algorithms. Here in this introduction lecture, we are only covering the basic high-level overview of the contents of the lecture. In the next lectures, we then will dive into specific models and also dive into specific tasks and cover the learning aspects of the machine learning algorithms. There's different types of learning, of machine learning, so it's so-called supervised learning and unsupervised learning. In supervised learning, we are giving examples, which Tom Mitchell called experiences, with target values, the so-called labels. So these targets can be continuous or discrete, and the goal is here to learn a predictor for inferring the target value for unseen data. So giving a lot of data with some labels, and you want to learn a model from this that enables you to predict the value for something that you have not seen in this training data. The unsupervised learning deals then with data that has no explicit target labels. So it's data which you want to analyze, where you maybe want to learn a generative model, so which enables you to maybe generate more data, but also to learn representations of the data. And recently to also enable then the supervised learning to do a better job by training some model unsupervised first and then train it later supervised. The two main tasks in supervised learning are the regression and classification. In regression, we are interested in getting for some input, here some vector and a d-dimensional vector, continuous output. So this is here the blue crosses are the training data, or the data that you use to learn the algorithm, and then for the red dot you want to predict the output of this function which you fitted in there. So here it's given by this by this dashed line. And the other important part is classification, where you have also again a vector that you give in as input, but here you want to have a discrete output, so some class label, some category like person, sheep, or something like this we had in this detection example. And here you can see you have a vector representation and you have a training a set where you learn the algorithms from, and then you want to, for an unseen example, predict what is the likely output for this vector here. But now, to give more specifics, we are now looking at the different parts of the machine learning model, so the data, the model, and the learning part. And we are looking here first at the data. So the first question when you want to learn a machine learning algorithm is, of course, where do you get the data from? So in research, we usually use benchmark data sets, which are available, so where we can download the data in the right format, which was provided by the authors of this benchmark data set. And the authors there ensured that the data is in a usable format. But the problem there is that when you download this data, then it's targeted at a specific domain or a specific task, and it may not fit to your thing. And it maybe also entails some data set biases, because it's just maybe taken outside, but you want to apply your algorithm inside or something when you have visual data, for instance. So then, yeah, you have to do something. And the thing that you can do, of course, is getting new data for the task and domain. So you're going around with your robot, but also maybe with your camera, take new pictures or record data with your robot. And then another thing that you also can do is that you maybe retrieve data from databases or get data from databases, or you maybe crawl the internet for images or something like this. But this is then, of course, something, in a way, very unstructured. Because when you get the data from multiple sources, so you gathered it from different databases and such things, then the data is maybe an incompatible format given. So in some database it's called like this, and in the other database it's called like this. So there's some structure missing that you need for your learning algorithms. And of course the data can also have different types of fields. So we can have categorical values where you have maybe something like red or green or whatever, so words which you have to map then to some numerical value, for instance. But you maybe have also strings there, which are maybe names, which you maybe have to deal with. You, of course, will also encounter missing values. So some examples don't have any values in there, or they are just null. That means that they are not set in this case. And of course, when you're dealing with real-world data, you will also have maybe misspelled values. When people are putting in data, then it will something happen that you have maybe something that is not in the right format. So one important part when you gather your data is, of course, to get it in the right format. So this process is called data wrangling. So here we want to transform the raw data into a usable format for the machine learning algorithm. And the main tasks are here the cleaning and the converting of the values so that you can use it for your task. And as said before, we are interested in numerical vectors, which is the format that we want to have for a machine learning algorithm. And there you have to, of course, handle the missing values. So, and for handling the missing values, there are multiple options available. So the easiest and usually best solution is to just replace it with 0, because it means ignore this value. But you can also go a step further, learning from the other values in this column, and maybe something like a mean that you can then impute there, or use a regression to learn something about these values. And the worst thing that you can do with missing values or with examples that has some missing values is to just drop the example, because usually you're in the situation that you have maybe not enough data, and every example that you can get from the internet is maybe, or from a database or something like this, is very valuable that you want to keep in the end. So usually the easiest option to just replace it with 0 is the best one. One important thing when you have the data gathered and you have recorded the data with your robot and you move it around, is really to visualize your data. So something like some summary statistics when you have some vector data is not enough. Here's some example. We have a data set X with vectors, which are here in this case 2-dimensional, and we extract from this some summary statistics like the mean and the standard deviation. And for this, For this point set, we have the mean given like this and the standard deviation given like this. And yeah, when you look at this data, so you plotted this in a two-dimensional plot, and you can see how it's distributed. And so what I want to show here is now that when you have the same mean and standard deviation, you can also have very different distributions and also maybe more insightful distributions of the points possible. For instance, something like this. Here you can see that the data are organized in a certain way. So that gives you already an indication maybe what are dependent variables, so or what is the dependency between the variables. So that can also look something like this. Here you have a dependency between the two variables, which then looks like this. So, and as I said, so the mean and the standard deviation of these two parts is exactly the same. So and the whole thing here is when you're not visualizing the data, you're maybe missing important things that are happening in your data. And something like this that you have here, because the mean and standard deviation could also be this dinosaur here. And so that's the whole deal of this example. So yeah, so also for image data, it's important to look over the data because you will have corruptions by yeah, some sensor failures or something like this. And as always in computing, if you put garbage in, you will get garbage out. So therefore, it's an important thing to also look at your data, which you put into the machine learning algorithm. When you have multidimensional data, so you have now not only two-dimensional vectors, but multidimensional vectors, then one option is to plot it here in this pairwise plot. So here we have 4 variables, and in each plot we are giving one variable with the other. So on the diagonal you get the summary statistics, which is here from this Seaborn pair plot. The summary statistics over the one example as histogram, but you get here also the scatter plots for two variables. And when you look at this, then you can already get something out of the data, and you learn the most when you visualize the data. And this shows you then the dependencies and the relations. So what we are usually dealing in supervised learning is with data that is organized as a vector. So we have examples that are given here in this set X as x1, y1 until we have n examples, and this X is a d-dimensional vector, and it's here called a feature vector. So this is usually the name that is used for these vectors. And then we have the each entry of this data vector is then called a feature or attribute or covariate. And the y variable in supervised learning, so in unsupervised learning we have no y, is called then the label or target response or annotation. In the following, we will always call the data specifically which is used for training a model, so that means from which we learn our machine learning algorithm, training set. So in here we will use xtrain for this. Here's some example what this might look like for some very simple example. So let's say we want to distinguish between apples and pears. So we want to classify these fruit images, and for these fruit images, because we thought about it, and we thought about pears and apples, and we thought like, yeah, most pears are somehow green, and the apples are mostly red, and they have a specific shape. And this we can encode in feature values which represent the roundness, so to say, as a ratio of a radii. And we can maybe determine this via using a half transform or something like this, so where we fit an ellipse to this foreground image pixels, and then get from this a ratio of the radii of the fitted ellipse as a feature that is between 0 and 1, which gives us then for 1 it's very round, and when it goes to 0 it's very narrow and not round at all. And And the other feature that we thought about is, or we now have for this example, is the redness of this fruit. So, and this is maybe all the red values over the foreground pixels and the average of this, and it can also be when it's totally red, it's 1, and when it's not red at all, so it has no red component in it, then it's 0. And the desired output, of course, is a label that is then 0 or 1, so in this case then apple and pear, and this is then usually called a binary classification problem because we have only 2 classes. Here we have some example how it may look. So we gathered from some image databases some images of apples on the left side and pears on the right side, and then we use our computer vision algorithm to extract the features, so the roundness and the redness. So here you see that this apple is very round, so it might get a 0.9, and for the redness it gets also very high value. When we then look at this apple, then we see that it's still very round, but here it will get a very low red value because it has mainly green pixels there. But when you then look to the pears, so our idea was maybe right here, that the pears are not very round in this case, and yeah, we have some reddish values, so we'll maybe get 0.5 here. But then we have also this Asian pear here, where we have a very round fruit, but also very high red value because the yellow color has also red components in it. So that might lead to a problem in the end when we then learn a machine learning algorithm. So and when we have then these feature vectors extracted, we can then visualize them. For instance, here in this plot. So we call this then the feature space, and each dot in this graph corresponds to an example which we extracted from an image. So the crosses, the blue crosses, are the apples here in this example. So we see that most of the apples are very round, and the pears are then the red circles here. And as you can see, on one axis we have the roundness, on the other axis we have the redness, and then you can see that this here is, in this case, this example. So it might look very different for other data sets or so, but just to give you an example how it might look. And given such data, we are then interested into learning a model. And this is the next part I want to cover. So what is the model about? So the model has different functions. We can have different views on this model. So we can see the model as some function that maps the d-dimensional vector to some output value, like the continuous value, or in the case of the classification to a discrete value. So we have here the functional view. So we just want to have a function in the end that puts out the desired target value. But we can also maybe ask for more. Maybe we want to have a probability distribution over all possible values for this given x. So on this probabilistic view is then to get the same output in the end to make then the argmax over all possible values, for instance here for the classification task. And the advantage of the probabilistic view is, of course, that we get also some confidence value in the end, which can tell us then if our learning algorithms in the end did a good job to predict this. It's the confidence of the predictor in the output value. So that gives us an indication how certain the predictor is in giving this label to this example. When we talk about models, we are talking also about parameters. So the parameters, which are usually in the following is also always called theta, are the things that we can adapt, which we want to learn from the data, and the model is specified by these parameters. And the amount of parameters is usually what is called then the capacity. So the larger the amount of the parameters we have in our model, the larger the capacity is, the more it can learn or can encode of the world. But we also have some other parts of the model which are not learned from data, which we have to set in advance. And these are called the hyperparameters. These are parameters that we can tweak without knowing something about the data. Or we can know something about the data, but we have to tweak it in advance. We will have shortly some example about this. So as I said, so the parameters are the values or the knobs in our model that we can tweak based on the observations that we have or the examples. And the hyperparameters are some values that we have to choose in advance so that our model can do something with this. And here's an example of a very simple approach to do a classification. It's the k-nearest neighbor classifier, where we just use as model the nearest neighbors. So we put in the training set, and to classify something, we are just looking for the nearest neighbors to our input example. So for the xn, we are looking just for the k-nearest neighbors, which is denoted by this n, calligraphic n with an index k. And for this, we want to find the k-nearest neighbors. And then when we look at a probabilistic model, then we can give the probability for a certain class by this equation. So we're looking over for a certain class C over all neighbors in surrounding of the given x and look how many of them have the class C. And then to make a valid probability distribution out of this, we have then to divide it by k. And in this example, the given hyperparameter, or this hyperparameter that we have to choose, is the number of neighbors, k. When we now look back to our apples and pear example, then we had here this feature space, and then we maybe have a new example, which is here this box. And for this, we want to figure out what is the class. And when we have k equal to 1, then we just look for the nearest neighbor. And in this case, that will result in that we find one neighbor, which is then a peer, so we would classify this image as peer. But when we choose a different hyperparameter, in this case k equals to 3, then we are looking for the 3 nearest neighbors. And this could be then, in this case here, these 3 neighbors. And as you can see, the majority of the pixels get classified as apple, so we would classify this in this case as apple. So you can see that the hyperparameter has much influence on the performance of the model or the output of the model in the end. So that means choosing the right hyperparameter is also a critical thing that one machine learning designer or machine learning algorithm designer has to do in the end. But coming now to the learning part of the machine learning algorithm. So learning the model means adapting the parameter theta, so given the training set. And in most cases, or often, it's maximizing the likelihood. So that means we want to maximize the probability of all labels given all inputs, such that this probability is maximized. And this is then the likelihood maximization. And the assumption that we can do usually is that the data is independent and identically distributed. So that means the examples that we extracted from somewhere or that we recorded or something like this are independent from each other. So the recording of one image at some point in time has no influence on the recording of another image or something like this. Or gathering one example has no influence on the other examples. And this then leads to the good fact that we can then factorize this distribution here, this joint distribution over the labels given the data into a product. And this, of course, then makes things a little bit easier, because then we can only reason about this product. And then the learning task is then the optimization problem. So we want to find the parameters that maximize the product of the probabilities, and this gives us then this theta star, which is then the learned feature vector in this case, the learned parameters in this case. When we now come back to the k-nearest neighbor classifier, then learning is very easy here because we just have to store the training data. But as you can imagine, as we increase the amount of training data, the complexity of the task to solve in the end, to look for nearest neighbors, will also increase. So this is maybe not a property that we want to have, so that we give the algorithm more data. It will take longer to do the predictions in the end. But the question in the end is, when we learn this model, how well does then the model perform? So how well can we then classify maybe unseen data or regress unseen data? And the other question that we might also have now, how we then choose this hyperparameter in a sensible way. And for this, we have to look at evaluation. So we evaluate our models on unseen data, and we measure the performance here. So measuring the performance is important because we want to figure out is our machine learning model generalizes very well. So that means, how does it perform on unseen data? Is it still as good as it was on the training data? So the thing is now, how do we measure the performance? For this, we are using some metrics. And some simple metric is so something like the training error, so which tells us how well we do on the to determine the target values for our given training values. But also we can look at the other metrics, and we will cover some metrics for specific tasks. So these are very task specific. Here in this case, we are just looking at the training error. But of course, the training error has the problem that, for instance, for our nearest neighbor classifier, this will, because we store all the training examples, will be 0. So it will not tell us anything about the generalization capability of the algorithm. The whole deal of learning is that we also want to reach in the end the training error of 0. So that means we still don't know what happens on unseen data. And for this, there's the concept of the training and test set. So we evaluate the performance of the machine learning algorithm on data that was not used for training. The data that we use for training, I already said, is called the training set, xtrain, or for learning the algorithm. And the other data that we are using for evaluating our algorithm is called test set. And usually the training data and the test set are independent from each other. So that means when we intersect both sets, then this should be empty. So we really want to have unseen data. So we don't want to measure the performance on data that we already saw in the end or used for learning. Important is here that we use the test set not for determining the parameters. So it's really a holdout set. So we don't use it at all. And one thing that is also important when you think about the test set is that you want to use it seldomly. So that means you don't want to use it so often, because this will bias in the end your design of the algorithm in the end. So and this is called usually the human in the loop phenomenon. So the test set is our estimate how well our algorithm is doing in unseen data. So that means by this we want to get an estimate how well our algorithm does with some real-world data. But you might be tempted to look at the test data and see how well your algorithm is performing on this. And maybe if you have even the test labels available, you might even want to compute the metrics there and then see how maybe different hyperparameter values maybe look on the test data. So it's important to note here that not using the data for learning and is the only thing that we want to achieve. So because when you look at your test data and you drive your decisions on certain parts of the algorithms using this knowledge about the test data, you will bias your model in a way that it's doing maybe better on the test data in the end, but it will not tell you anything about the generalization capability in the end anymore. So that means your algorithms is then maybe doing, after some tweaking and some fiddling around with the hyperparameters, maybe doing very well on the test set, but when you then take your algorithm your good algorithms to the real world, it will fail miserably. So even though you're not using the parameters directly, you're using indirectly, and you maybe bias the result in the end. So the question is now, but how do we then choose the hyperparameters in the end? And for this, comes in the validation set. So selecting the hyperparameters should usually happen on the so-called validation set. So the validation set is apart from the training set. We split it up and treat it like our fake test set, so to say. So we are using this to then evaluate the performance of unseen data, so to say. The advantage is, because we are now using not the test data in the end to tweak our hyperparameters, we can use this to figure out how the algorithm is maybe doing on not data that is used for learning. But the advantage is that in the end, when we tweaked our hyperparameters and we made all our decisions on the validation set, we then can take the test set to get then the real performance on unseen data. So, and then we will know something about the generalization gap between training and test set. The important part is here also that the validation set is not used for training or for fixing it's used for fixing the hyperparameters, but they are not used for learning. So when you then have fixed maybe your hyperparameters, then it's also possible to just use the data with this fixed hyperparameters and to train your algorithms with the additional validation set, especially if you have only a few examples for your training. And the important part is that the validation set is not the test set, so that's important. And when we come back to our example from the apples and pears, then this might look something like this. So when selecting now the k, then we can look for the k that minimizes the validation set error. So the error is given here by the number of examples which are incorrectly classified or incorrectly predicted. With the here in this example with the classification, so where the y hat is given by the argmax over all classes, as noted before. So it's the number of wrongly classified examples divided by the number of all examples that we have in our training set. And then when we plot for instance for this k nearest neighbor classifier, our training error, then we will see when we have just one neighbor, then we will have zero training error, and when we increase the k, then we will see that the training error will increase, because it will not do maybe the correct job anymore for all the training data. But what we also can see is that maybe with one neighbor we have maybe a higher validation set error, and by increasing the k, we can also plot here the validation set error, and it usually looks like this, that it goes down, and at some point with the hyperparameter it goes up again. And we want to choose basically the k that leads to the best performance also on the validation set. In this case here, maybe the five neighbors. So and this is how you choose your hyperparameters. And since I think this is the most important part to note or to not do when you're designing your machine learning algorithms, or when you want to learn good models for real-world applications, not to use the test data. So therefore I put it here again, that you don't use your test set for tuning your algorithms. So by whatever training models with different hyperparameter selections, or differently long, and then whatever, look at the test set error and then do this over and over again, and this will not lead to good performance in the end. It will also not lead to an algorithm that generalizes well, so in the end. So you will need to have some test set evaluations, but you should not use this to drive your decisions about the model. So therefore, we have this validation set available. When you now train your algorithms and you maybe can decide when to stop or something like this with the training, then you should do this decision just solely on the validation set error. Because this is also something that is maybe available for everyone. So you should treat the test set as something that you are not getting when you want to have it in the end. So because it is some approximation of the thing you learned your machine learning algorithms, you put it on a platform, and then you go out and then you get new data. And this is the role of the test set. And I'm saying it again, so all hyperparameter choices should only happen on a validation set. So this is the main message that I want to convey here. So don't fool yourself by making the wrong conclusions by tweaking your model that it gets a very high test error. And maybe not then a low validation set error, because it maybe leads to different decisions in the end. And with this, I'm coming to an end. So in this lecture, I just gave you a high-level overview of the different parts of the machine learning algorithms, which were the data, the model, but also the learning parts. We didn't dive too deep into specific models. So I gave you an example of the k nearest neighbors, which is a very simple classification model. But along this, I hopefully introduced some machine learning terminology, which will be needed in the rest of the course. But we will, of course, cover much more terminology and basics in the upcoming courses. And here we had only a high-level overview of the machine learning pipeline, and covered aspects like training set, validation set, and test set. More on these practical aspects will also come then in the tutorial, where we have the possibility also to discuss about this stuff. And in the next lectures, I will then cover regression and classification models. So these are the upcoming 2 lectures, and then after that we are diving also into unsupervised methods, but then come also at some point to the deep learning models. And in the rest of the courses we then cover more complex models, but also how to learn them and give you insights on this. So with this, I'm coming to an end. Thank you for your attention, and then see you next week.